So today I'm going to talk about our collaboration with a Volvo company. This is Volvo Group. We have been having series of projects with them, and it generated a kind of series of work that might be interesting for this community, I think. So when we talk about predictive maintenance, simply we want to identify failures and act upon them and do some action that prevent them before they actually happen. And when we look at the success stories in the field of predictive maintenance, we see, for example, two different very successful ends of the production. When we talk about critical and expensive equipment, such as airplane, then there is lots of high quality data available in such an environment. And that as a result, we will have kind of good maintenance plans and activities. And then on the other hand, when we are working with a simpler component that are contained, and often we can integrate some physical knowledge in them, like ball bearings, we also see a lot of good, successful stories. And often in these cases, we have a good understanding of the failures that are happening. So this is what I see as successful examples of predictive maintenance. But actually, the complexity spectrum is wider than this too. For example, the application area that we are working with Volvo trucks is something in the middle. It's not as simple as ball bearing, and it's not as complex as, for example, airplane maintenance. But on the other hand, the complexity comes from other aspects. And it's not the only example of this being in this spectrum. For example, we see other machineries in the smart cities and so on, that we have very little control about data collection and the environment of operations. So in particular, there are two main challenges for this application area. One is we have to work with the existing data. And often the existing data is not the quality that we need. Sometimes we don't have a perfect sensor installed in a perfect component that we are looking at. And also the frequency of the data and so on, they show a challenge. There are so many variety on different parameters that we can look at. And then another big challenge is the external conditions. So trucks are operating in totally different environment. For example, a truck operating in Spain behaves totally different from a truck that operates in Norway, basically. Both weather condition and also topographical conditions and so on. Another thing is we have also like mixed fault symptoms in these circumstances. So if you want to solve such a problem, especially now with the availability of, like we see advancement in AI models like ChatGPT, then we would look at the methods that are self-aware. What do I mean by that? So then we would like to build models that they can automatically understand what is normal, what is not normal, and find interesting patterns within this data. At the same time, they build with existing data. That's perfect, like language models. This is an ideal model. And such a model, on the other hand, for predictive maintenance, would be good, for example, for detecting the faults, but then probably cannot explain what are those faults related to. So the good thing is, such a model will not be kind of fine-tuned only for one particular fault definition, but on the other hand, it's will be difficult to identify which fault it corresponds to. So this is one of the early works that's it's developed actually in our lab, and I haven't been part of it, but it has been, we are still working on it and we still use it in several different applications. So I think it's a good example of showing this. So we want to develop a system that understands this operation and basically work with undefined fault types. So the idea is based on something we called wisdom of the crowd. So what we think is majority of the data is normal. So let's say if we have a population of buses, majority of them will behave normal, isn't it? So then if we can create a model for the majority of the data, then that should be kind of good enough for describing what is normal. And so the idea would be we collect several sensor signals from vehicles, and then we create a model of what is the typical behavior of these machines. The good thing is such a model will be robust, for example, to seasonality, because when you create a model comparing comparing to the other vehicles, then you are modeling it as time passes. So this kind of adaptive model. And then we try to do it in a different ways. So the simplest paper, the first paper that I'm citing here, used something called histograms. But then we extended it to the other deep learning neural network that describes this normal behavior. So there are a series of papers on this topic. And what happens is when a new vehicle comes, we want to see if this vehicle like behave normal or not normal. Then we compare it with a model that's created based on the majority of the vehicles. And then we calculate some sort of a deviation level from this comparison. So this is one of the ideas I had, and then we implemented it with a fleet of buses operating in Kungsbacka. It's a small town in Sweden, and there were like 19 buses. We managed to, based on the data, mark potentially a fault. Like we figure out that there is a vehicle that behaves differently from the rest. And then we asked the workshop personnel that this doesn't seem to be right. And they check the vehicle. They say, oh, no, actually, it's pretty okay. We went home. And then few weeks after, there were complaints that from the driver. And also there was like, they had to do the service kind of for the regular service twice for that vehicle. So there was something wrong. And but then the wrong thing was the fan was overperforming, so not under. So that's why it was not detectable with a normal fault detection scenarios. But then that was kind of ideal scenario, and I think that's where we are going to. But what's currently happening in the industry is it's using supervised learning for predictive maintenance. By supervised learning, I mean we encode the problem either as a classification task to detect or faulty versus normal, or remaining useful life prediction. And the good thing about this approach is it's easy to evaluate. So we can use normal accuracy measures, FS-score, and so on to understand the performance of the model. And then also it's easy to deploy, and it will work with a lower quality data. It does not need high frequency data because we don't retrain as often as the other model. And but then there is a challenge with this from application point of view that we basically learn what human does. We don't do better than that. So we learn the past repair histories, and that's, I mean, it's good for automation, but it's not good for improvement of maintenance. The work that has been done in this area was basically you have series of data points from different vehicles. So imagine in the y-axis, we have different vehicles. Then we mark some of the data before a failure happened as faulty data, because we imagine that they carry informations, indications of the faults. And then we mark some of the other data like this as healthy data. We have to select some, and then we create a data set. Then we define as a classification task or regression. And then we try to find a difference between these two class labels. I mean, it can be two, it can be a lot more. So I'm just simplifying by saying two. But then it can be done for almost different type of faults and so on. And then you need some feature analysis, some balancing of the data to manage such a work. And that's one of the things that currently has been deployed and used in the company. But then Another example I want to bring in here is estimation and predicting the state of the health of batteries. We tested this with my PhD students for hybrid buses. So this is also pretty simple. So formulating the problem as regression, and then we try to estimate based on right selection of the data, we could perform better than if we use all the data available. But when it comes to real world, we always have a challenge of generalization. When we worked, for example, one way of handling such a generalization in working with the features that are invariant to the changes that are happening in different domains. And for us, we tested this state of the health, estimating a state of the health of the batteries with some sort of feature extraction techniques based on genetic algorithm. And then we showed that if we select the right features using genetic algorithm, for example, then we were able to improve the results in when dealing with different domains, rather than if we just merge the data in one kind of box, we would get worse results. And then another interesting finding here was, for example, in these settings, when we had more diverse data for training the models, then those models usually were more adaptable to the new scenarios than when we had very little or narrow type of data. So, for example, generalizing when we had a combination of single decker and double decker to articulate it was much better than when, for example, we had only double decker and articulated data and we wanted to test on the single decker, because the performance of them were so different from the single decker buses. So yeah, in theory, by selecting the invariant features, we were able to improve the accuracy and decrease the error. Another thing that we have been working on is domain adaptation. That's also aim for generalizability of the models. Oops, I went too much. Yeah. So in this setting, what we were thinking of was not only considering two domains that are different from each other, but having multiple domains. And what we were interested in was doing this for regression task, which is again was the estimating the state of the health of the batteries. And for example, beginning of my talk, I mentioned that we see a huge gap or difference when we work with the data coming from the trucks that are operating, for example, in Spain versus the one in Norway. So how can we create models that can work for both of them potentially? That would be the ideal scenario. And what we did was we proposed the new model based on contrastive learning. So the idea was we get the data, the domains were known basically here and they were suggested by the expert. So we would get data from different domains, and we did have also the ground truth here. This is supervised. So we had also the information from a state of the health of the batteries at that point. And then what we would do is, given this data point, that we would the data points that they were close in the different domains from the state of the health perspective, we wanted to be close in the representation space. So that was the idea behind this. And what we did was we showed the performance of this domain adaptation, for example, for two domain first. And we got pretty good results. For example, after domain adaptation, the results below shows the result after domain adaptation in the source domain and in the target domain. And as you can see, our method, which is the green one, matches better the ground truth, which is the blue one, in comparison to the state of the art. We didn't stop here. We tested it in the real world data as well. So if you look at the plot on the right-hand side, you see this transferring between double-decker and single-decker. So when we train combining all of the data in one pool, we got the error that was the orange line. So the model was not performing perfect. And when we train and test only on one particular class that we didn't have a lot of example from, for example, double-decker, then we still, although they were homogeneous kind of category, we didn't get super good results. But when we used domain adaptation and then tested it on the double-decker data, suddenly we got much better results. So it works. Sometimes it works. Another scenario that we tested was domain generalization. So we got data from all different countries, and then we create a model using the same technique of domain adaptation, and using all of those data from different countries. And the result showed that we, at the end, perform better than baseline training for each of those countries separately or combining data all together. So we managed to outperform all of this, which is the purple line, purple bars in this plot. Another way of working with predictive maintenance is analyzing survival patterns. I don't know how many of you are familiar with that, but basically this is something that's used mainly in the medical domain, that you try to understand the survivability of a group of population of equipment or people or yeah, and or trucks. And you want to see, like, when is the best time that I do, for example, maintenance, looking at the population, basically. So the good thing about survivability is it looks at the data that are censored. By censor, I mean, we have trucks that suddenly, after like few years of being in a study, suddenly they drop from study. Usually when we do normal machine learning, regression or classification, we get rid of that data. We think, oh, we cannot use this instance anymore. But in this case, we could incorporate that knowledge. This is still a knowledge, you know, that can be incorporated in survival analysis. And also, like what we looked at, the difference here is with usual classification and regression is we usually get a curve as a result, not a point, like not a prediction accuracy, for example. And so we again tested it for this battery replacement data set that we had. And we also tried to explain the results for the expert. Just to tell you a little bit, on the plot on the top right, on the top left, you see all different survival patterns that exist for different vehicles. So per vehicle, we could have a curve using the existing survival analysis method, for example, random survival forest. And then what we clustered them into these common patterns. And the reason that on top of this kind of clustering, we try to explain them using SHAP values. If you are familiar with SHAP values, it's one of the existing techniques for explainability. But the difficulty we had was SHAP value is for the point estimates, not for explaining a curve. That's out of the question. So that's why we had to first create another proxy model on top of the curve models, and then use explainability for that, the proxy models, not the original survival curve analysis extractions. But then, if you have worked with SHAP value, you know that they're not that explainable. Okay, you understand, for example, that here in this pattern 1, which is one of the best patterns that they have, they basically didn't have any failure. The emission level is important. And if you're in truck business, you know that after a certain year, now we are in a new emission configuration in compared to many years ago. So of course, that should be one of the main important parameters, but the expert knows this. So what else they will get from this? So that's why we started to look at something else, which is called counterfactual explanation of survival patterns. So the idea here was, okay, let's say I'm in the pattern type 9, which is the worst, how can I do better from now on that I end up in pattern number 3? Can I change something? And then, of course, you don't want to suggest things that are irreasonable. For example, you don't want to tell the vehicle, become younger, you know? So you want to limit the possibility of the suggestions that you're getting. You want actionable counterfactuals. You want to do plausible. And also you want to do minimum changes. What is the minimum thing I have to change that I can operate a bit longer? My life ends, for example, in this time or these operating hours. How can I change it that I work slightly longer, 6 months more? So that would be the idea behind this work. And it's actually published this year, so it's very recent. Overall, what I wanted to talk about today was we want a dream solution. We want a system that can explain itself. So that would be the ideal predictive maintenance solution. What comes close to it would be this idea of the wisdom of the crowd. And what actually practically works in the company, we have seen supervised learning has been having very good result. And then in order to generalize it, we use domain adaptation, transfer learning, or other meta-learning and so on. So the other possibility of making sure that the solution works for several domains. And finally, we need explainability method to understand the solutions. That's it for me. So hope this is the future. Thank you.